Hey guys, good morning all. Just give me a in the chat if you guys can hear me and see the sublime text. Quickly give me as the chat if all of you guys can hear me loud and clear and you guys can see the sublime text. All of you can. Cool. Let's quickly start with today's session. Today we are going to continue with our trees. That's what we started in the last session. In last session, we've also finished our last topic, which was backtracking. So let's do a quick revision what we covered in that, and then we'll start with trees. So in backtracking, we have covered questions already, 4 questions prior to that. Fifth question, which is rat in a maze, which is technical variation of 7 to 8 variation, is what we did. The problem statement was you're given a matrix. You need to find the possible path in a 2D matrix. So the task is to check if there is a path from source to destination. So in the matrix, one cell is considered to be source, one cell is considered to be destination. There are some safe cell and some blockage cell. Safe cell means you can pass through it. Blockage cell means you cannot pass through it. Obviously, source and destination will always be a safe cell. There are directions that you can move in. You can move up, down, left, right. There are constraints that you can move in terms of matrix. Okay. All right, we talked about this test case. If the path is possible, you return true, otherwise return false. Remember, you don't have to print the path or count the path. You just need to tell whether it is possible or not. So even if there is one path, you return true. No path, return false. Moving on to the variations of it. Before we even move to the solution part of it, one thing if we have to travel in a matrix, we talked about something which will be very handy to us called direction matrix or direction mapping. What is direction matrix or mapping exactly? If your current state is I, j in a matrix, what will be the new coordinates if you take directions? So if I take 4 directions, this will be my new coordinates ij plus 1, I, j minus 1, I minus 1j, I plus 1j respectively. Similarly, if I take diagonal direction, these will be my new coordinates. Okay, so we make a mapping out of it. That is what we call as direction mapping. Now, how to solve such kind of a problem? There's a real life example to understand that. So real life example is, we can think of a hiking example with storing path and marking visited path. What do you mean by storing path and marking visited path? Let's say you start from a source and you have to go to a destination. You're going to mark the path that you've already traveled, which are not linked direction. So you don't keep visiting them again and again. Once reached the destination matches your coordinate that you were looking for. That is when you know you have reached the destination. Okay. So if you have to convert into a programming question, how will that look like? You start with the queue, which stores the current cell I, j for keeping a note of path. You insert the source, which is 0, 0 in the queue. You run a loop till queue is empty. You check for all the paths while doing backtracking. That's exactly what backtracking is. You mark all the cells traveled as visited. If you reach the destination, return true, otherwise return false. Then you move to variations of the question. First variation was the basic variation. Start source is 0, 0. Destination is m minus 1, n minus 1. Direction becomes 4 directions. Okay. So there are ways that we can actually code in. We can write in a multiple logic way of recursion, but we prefer to code it iteration. Why did we prefer it? We already talked about it in terms of saving the time complexity. Now, here we define a direction matrix. We mark all the cells as not visited. We create a queue. We append the source. While my length of queue greater than 0 means that till I have not exhausted all the path, I am taking my current pair, marking the current pair as visited. Check if I've already reached the destination. If I have, return true. If not, then continue with the backtracking part. While I'm backtracking, I'll take care of the boundary conditions here. If I have reached here, means outside while loop, I have exhausted all the possibilities, path does not match, I'll return false. Okay. All right, we talked about 7 variations of it. First 5 variations were based upon change in source, change in destination, source is constant or source is varying, destination is constant or destination varying, etc. etc. Okay, all the directions are changing. Variation 6 and variation 7 are very useful. Variation 6 has been asked in Google is where you are taking exactly case steps per time. Not at max case steps, exactly case steps. Okay, and variation 7 is not been asked in any company yet, but it is a very high likely chance it can be asked. It gives maximum case steps. You can take any number of steps between 1 to k. Okay. Then we move to the implementation part here. The first way is finding a brute force, which is you can talk about this way, or you can talk about the optimized solution, which is big of length of direction matrix. Okay. I told you to try some questions for homework. Retina maze is available on as it is on LeetCode Geek for Geeks and Hacker Rank. There's a very similar question like retina maze called connected islands on LeetCode as well. Okay. Then somebody asked the question for recursion versus iteration. I gave you the answer. In what case you should prefer recursion, what case you should prefer iteration. Okay. Finally, we start with the next topic, which is called trees. That's what we're going to continue for today's session as well. As I always say, if you want to become master in data structure algorithm, know 3 things about it. What is the use case? What is real life application? How it is going to be coded and implemented. Okay. First thing first, before even jump to trees, let's clarify the difference between a linear data structure versus hierarchical data structure. Certain data structures are called as linear data structure. Certain data structures are called hierarchical data structure. What's the rationale behind it? What's the reason to define linear versus hierarchical? Is it because they're stored in contiguous location? That's why they're called linear. That's an incorrect statement. There is more than one logical way of traversal. That is when you club them as hierarchical. Okay, take an example to understand. If I talk about any linear data structure, arrays, linked lists, tags, queues, there's a specific way of traversal. Okay, either horizontal or vertical. In a hierarchical data structure, it's more than one logical way you can traverse them. Means in terms of a DFS or BFS. And when it's hierarchical, any data structure which clubbed is hierarchical. So your trees, graphs, tries, etc. etc. Okay. Usually you have at least two different ways. Either you can traverse on their depth or you can traverse on their breadth. If I talk in context of trees specifically, there are three different type of DFS: pre-order, in-order, post-order. BFS is only one type, which is level of traversal. Okay. Second part is we understood tree versus doubly linked list. So a lot of people confuse the concept of doubly linked list versus trees because doubly linked list also has two pointers. There's a difference between how doubly linked lists work. Doubly linked list has a two pointer, which is completely correct. So B dot previous is A, B dot next is C, A dot next is B. This is completely correct. But there is no parent-child relationship. There is no parent-child relationship, and all nodes are on the same level. In the case of a trees, there is a parent-child relationship and there are nodes on multiple levels. So root has a child has subchildren. We don't call it subchildren. I've just made it for the understanding. What do you mean by subchildren? Okay. The children which are under the tree or the children which are under the children of root, that is what we're referring as subchildren here. So we try to understand here also I have two pointers, but A dot left becomes B, A dot right becomes C. There is a parent to child pointer, but there is no child to parent pointer. If tree contains cycle, means if there is a parent to child as well as child to parent, then it will not remain a tree anymore. It will become a graph. Okay. That is something that we discussed in the last class. Today we are going to start with types of trees and we'll continue forward with the questions. Okay. More theory and then questions. But before I start with today's session, quickly give me clear if everybody's crystal clear. Any doubts, any questions, please let me know. Come on, guys, quick in the chat. All good with the revision? Good. Let's start with the type of trees. Now, type of trees, we can classify it in two types: binary trees and n-array trees, which you call as generic trees. Generic trees. Now, what is binary tree? Let's talk about it in detail here. The name binary itself tells it has to do something with two. So, a tree with maximum, remember the word maximum here, of two children. Maximum of 2 means either 0 or 1 or 2 for each node is called binary tree. Okay. A tree with a maximum of 2 children, 0, 1 or 2 for each node is called binary tree. So there are certain concepts like leaf node. Leaf node is a node which does not have any children. And what do you define a complete or full binary tree? A complete or a full binary tree is where all the non-leaf nodes will have exactly 2 children. Okay. We'll talk about a property, but I'll go to that property a bit later. Let's understand the terms that we have talked about. Okay. First thing first, what is a binary tree? A tree with a maximum of 2 children, which is 0, 1 or 2 for each node is called binary tree. Then there is something called leaf node. What exactly is a leaf node? A node which does not have any children, that is what you call as leaf node in a tree. What is complete or full binary tree? We know the definition of binary tree, but what is complete or full binary tree? A complete or full binary tree is that tree where all the non-leaf nodes will have exactly 2 children. Okay, let's try to understand that by multiple examples. If I talk A, B, C, D, E, F, and G. Okay, now, first thing first, is it a binary tree? Let's answer that question. Then we'll talk about what are the leaf node. Then we'll talk about is it a complete or full binary tree. Okay, let's start number one. Is it a binary tree? Come on, guys, look in the chat, true or false. Does this qualify as a binary tree? The answer is yes, it is true. Why? Because every node should have at max 2 children. So if you take any node of this, either they will have 0, 1 or 2. Max 2, the criteria is 0, 1 or 2. Each and every node classify each and every node satisfy this category. So it is yes, it is a binary tree. Number two, what are the leaf nodes here? Leaf node is a node which does not have any children. So the node which does not have any children is D, E, F, and G here. Okay. Is it a complete or full binary tree? True or false? The answer is yes. It is complete or full binary tree. Why is that? Because non-leaf nodes means the node which are not exactly leaf nodes, so becomes A, B, and C. They should have exactly two children each. A has two children, B has two children, C has two children. So that is why it is a complete or full binary tree. All clear? Cool. Let's move to second test case. This is example number 2. DEF. Let's make this node as null. Now, is it a binary tree? Is it a binary tree now? Yes, it is still a binary tree. Why? Because every node is still satisfying maximum to 0, 1, 2. What are the leaf nodes now? D, E, and F are the leaf nodes because G is not a leaf node anymore. The G is not node anymore. So D and F. Is it a complete or full binary tree though? Let's see. If it's a complete or full binary tree, means all non-leaf nodes should have exactly two children. So A, B, and C should have exactly two children. A has two children, B has two children, C has only one children, or C has only one child. In that case, this condition becomes false. Okay. Now, once we understood the concept of binary tree, leaf nodes, and complete full binary tree, now we can talk about the property, which I said I'll talk about. Property is for a complete or full binary tree, the number of nodes at height h is 2 raised to the power h. The number of nodes at height h is always 2 raised to the power h. If that condition is followed, you can understand it's a complete or full binary tree. So let's take an example. We start with h equal to 0, by the way. If I start with h equal to 0, 2 raised to the power h would be 1, which is one number of node. If I start with h equal to 1, 2 raised to the power 1 will become 2, which is 2 number of nodes. If I start with h equal to 2, 2 raised to the power 2 become 4, which is 4 number of nodes. This satisfies the category, that's why it's a complete or full binary tree. If I talk about here, h equal to 0, 2 raised to the power 0 becomes 1, which is correct. H equal to 1, 2 raised to the power 1, which is equal to 2, which is correct. But if you look at h equal to 2, 2 raised to the power 2 equal to 4. This should be the number of nodes at that layer or at that level if it was a complete binary tree, which is not satisfied here. That is why it is not a complete or full binary tree. Everybody clear? Quick in the chat, guys. Cool. Let's move on to example number 3. I can just take this guy. Let's move on to example number 3. We are still testing about the full binary tree or complete binary trees. So let's take this guy. Example number 3. A tree containing only one node. Is it a binary tree? Yes or no? Is it a binary tree? Okay, I got the answer no. What about other folks? Come on, guys, quick in the chat. Is it a binary tree? Some of you are saying yes, some of you are saying no. That's confusing answers. What's the property of binary tree? How do you define a binary tree? Maximum of 2 children per node. Do I have a node here? I have a node here. Maximum of 2 children means either you can have 0 or you can have 1, you can have 2. You cannot have negative for sure. A is a node which does not have any children, which is condition is satisfied. 0 is also part of 0, 1, and 2. So output is true. It is a binary tree. Everybody clear? Those who were saying answer no, it is a binary tree. Okay. Number 2, what is the leaf node here exactly? What is the leaf node here? The only node which is a root node is my leaf node. What next? Is it a complete or full binary tree? Definition of complete or full binary tree is non-leaf node should have exactly two children. So I have only one leaf node. I don't have any non-leaf node. So condition is satisfied. You can also verify it by 2 raised to the power h, which is going to be 2 raised to the power 0, which is 1 here. So output becomes true. Okay. Let's move on to next. Example number 4. Now let's talk about A, B, and C. Okay. All right. Is it a binary tree? The answer is yes, it's a binary tree. Okay. Is it, what are the leaf nodes here now? Leaf nodes are just B and C here. Is it a complete or full binary tree? Definitely it's a complete or full binary tree. The only non-leaf node have exactly two children. And you can verify by this. You can verify by this 2 raised to the power h condition also. Okay. I think this one is sufficient enough to walk you understand before I move to the inherit trees or generic trees. Let's quickly revise what we discussed. In the type of trees, the first category of type we already covered, which is called binary tree. There is a special kind of binary tree which is called as binary search trees. We'll talk about it once we complete binary trees, then we'll move on to the binary search trees. Okay, so I'm not covering it here. So two type of trees, generally binary trees and n-ary trees. Binary tree means maximum of two children for each node. That is what we call as binary. Leaf node, which does not have any children, complete or full binary tree when all non-leaf node have exactly two children. Also, quickly check if you want to check whether it's a complete or full binary tree, just check with the height h. At height h, number of nodes should be 2 raised to the power h. Okay. So it's binary tree, leaf node, we test with example number 1, example 2, example 3, and example 4. Everybody crystal clear with this? Okay, cool. If this is clear, let's talk about n-ary trees, which is generic trees. So generic means a tree with a maximum of n children. Did you understand example 2, maximum of 2 children? Example 2. Yeah, what's not clear in example 2? Line number 80 is not clear. Is that what you're asking? Is line number 80? What is a binary tree? 82. Okay. So the definition of a complete or full binary tree is all non-leaf nodes should have exactly two children. Okay. So non-leaf nodes are D, E, and F here. Okay. So A, B, and C should have exactly two children. A satisfies the condition, two children only. B satisfies the condition, two children only. C does not satisfy the condition because it has only one children. That is why written false here. Okay. Maximum of 2 is for binary tree. Exactly 2 for non-leaf node, that is for complete or full binary tree. Okay. It is a binary tree for sure, but it is not a complete or full binary tree. Got it? Cool. Now coming to the n-ary tree part. So what exactly is n-ary trees? N-ary tree is something that we call as generic trees, right? So we're not talking about binary per se, we're talking about any value of n. So n-ary trees, a tree with a maximum of n children, which is 0, 1, 2, 3, 4, 5, till whatever value of n for each node is called n-ary tree. Okay. Now, what do you mean by leaf node? Leaf node is a node which does not have any children. That definition is still same. Which one do you call as complete or full n-ary tree? Is all non-leaf nodes will have exactly n children. Okay. All right. Let's talk about example 1 first. A, B, C, D, E. The order is completely messed up, so I can't say which is A, B, C, D, E here. You can say what's the children of B or what the children of C, that is not clear. B and C are children of A, that is clear, but if you're referring is as A, B has two children, D and E, I mean, at least that's what I can see in the Zoom chat. And this is C. Is that what you're referring? Is that your tree structure? Okay. So all non-leaf nodes should have exactly two children. So D and E, they have, what are the non-leaf nodes? The non-leaf nodes become A and B. C does not satisfy the condition for it. So you will have 2 raised to the power 2. This is not a non-binary. The answer is no. It's not a full binary tree. Okay. All right. Let's move on. Now, completing to the n-ary tree part. So n-ary tree, if I take an example of n equal to 3, let's make A, B, C, D. And if I have to make 3, E, F, G, H, I, J, K. Okay. Let's start with first thing. Is it an n-ary tree? Come on, guys. For n equal to 3, is it an n-ary tree? Quickly in the chat. The answer is yes. Why? As per the definition, maximum of 3 children per node, which is satisfied. Maximum 3 children per node is satisfied. Is it a complete n-ary tree? The answer is no. Why? Because then it should be exactly 3 children for each node. So A has 3, B has 3, C has 3, C has 2, D has 3. This is fine because these are leaf nodes. C has 2 children, that's why it is not a complete or finally finite tree. Let's take this. Example 2. B, C, D, let's say O. And here you can say about P and Q. Okay. So is it an n-ary tree? And then we'll talk about complete n-ary tree quickly in the chat. Is it an n-ary tree? The answer is no. Maximum of 3 children per node. A has 4 children. It is not an n-ary tree. Is it a complete n-ary tree? If it cannot be n-ary tree, it can never be complete n-ary tree. It's a subset always. Okay, so output becomes null. Now, just for a context, how do we write that in the code for n-ary trees? We're not writing the code here. We'll write the code once we move after completing this theory. You just write node left comma right, 2 children for a binary tree. Okay. If you have to make it for an n-ary tree, you make it as a vector of list or array list of node, name it as children, and you initialize the values with null, so and so forth. Okay. This is for n children, which you call as n-ary tree. Okay. Everybody crystal clear with this? Quick in the chat. One guys, be quick. Alrighty. So what have we talked about so far? We talked about what part, and we talked about, well, technically only the what part. Now we're going to talk about, one moment guys. Now we're going to talk about applications of trees, and then we'll continue for it. So next topic is applications of trees. We covered the type of trees and what are trees. Now we're going to talk about application of trees. Yep. Can example to be treated as n-ary tree if n equal to 4. N equal to 4, maximum of 4 children per node, yes. Then it can be treated. Okay. Alrighty. Let's move on to applications of trees. So first thing first, tree as a data structure you have been utilizing quite a lot in software engineering, which you may or may not have noticed, but you have been using it quite a lot. Let's try to understand that. You might have heard of any file storage system, no matter whether you're using a Windows or a Mac or a Ubuntu or Linux-based systems. You will usually see a structure like this. There is a drive, inside that there are folders, let's say C, D, E, and F. And let's say inside folder A, or a particular folder, you have, let's say, image, You have, let's say, video. Let's say you have GIFs, and you have maybe something else, whatever it is. Okay. The path of any file, when you do a pwd as a command to find out the path, it's always like parent folder, subfolder, folder 1, folder 2, etc. All agree with this? That's how the file storage system or the path of any file storage system looks like. Quick in the chat. How is this being quick by? There's a root. The root has children. You're traversing some children inside that root. And root can have multiple children, as you see here. This is a hierarchical nature. This is implemented by trees. Hierarchical order. This is implemented by trees. This is a real-life application of trees, file storage systems. Number 2, ordering. When you say ordering, there is a type of binary trees which we call as BST, which we'll talk about in some times once we complete the binary trees. Their search and access is faster than arrays and binary trees. Okay. What do you mean by that? Let's compare. Complexity of insertion and deletion. You have arrays. You have, let's say, BST, and you have linked list. In arrays, it is big of n. In binary search tree, it is log of n. In linked list, it is big of n. Okay. Fourth, there is no upper limits. What do you mean by upper limit? Since it's a dynamically created data structure, you can add as many nodes as you want. You can delete as many nodes as you want in a runtime. Array, static data structure, it works up to a limit. Linked list, no limit. You can create as many nodes as you want, delete as many nodes as you want. Same goes for trees, no limit. And why does that happen? That happens because it's a dynamic allocation. Means you can increase or decrease size of tree at runtime. Okay. All right. So these are the application of trees. Talking about the file storage system, it follows hierarchical order. Some of the trees are specifically used for ordering purpose, which we refer as binary search tree, which we'll talk about further. The complexity of insertion and deletion in binary search trees is better than binary trees and arrays, which is log of n. Okay. Arrays is big of n, linked list big of n. It's not upper limit because of the dynamic allocation we talked about. So you can add and decrease the number of nodes in your trees. Now, moving to the final part, which is the code part here. Code is important. Let's talk about it. The code of the tree is super simple, but that's super simple. You need to be crystal clear of the understanding. That's when you can understand to super simple. Okay. While linked list deletion insertion is one, maybe it's when also if inserting in middle last. No. Provided you're given the node where you have to insert and you don't have to traverse there, that is when you call big of n. Okay. Obviously, you cannot have a random access in a linked list, but if you're given a node where you have to insert and delete, that's always big of n. Okay. Now, coming to this part. To understand the code of binary trees, you need to go back to linked list. If you understand what's exactly happening in a linked list, code of binary tree becomes a cakewalk to you. Okay. So I'm going to take you back to maybe 1 month or 2 months back when we started covering linked list. I'm going to write you some line of code which you have already done a lot of questions on based upon linked list, if you guys remember it. And we are going to backtrack there to understand something important. That schema that we define for a linked list is something which we'll be using exactly same for linked list, exactly same for binary trees. Okay. So let's go back to linked list. I'm going to take a piece of code which we discussed in detail at that time. I'm going to write it here again. Binary tree and binary search trees we'll cover later. Let's complete binary trees because binary tree is a superset, binary search tree is a subset. We'll talk about it once we're done with binary trees. Okay. In interview, both are asked, so we'll discuss both the questions. Integer data node next equal to null. Python we had something like this, underscore, 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 init self dot data, self dot data equal to data, and self dot next equal to null. And struct node, you have integer data, you have node star next equal to null. Okay. Do you guys remember this piece of code? We had a detailed discussion over this once we started linked list. Yes or no? All of you guys remember this code? Cool. If you remember this code, well and good. I've written the code specifically in all the three languages, Java, Python, and C++. So if you remember, we did discuss it in detail at exactly the same format that I'm discussing right now. What I want you to revise is, or remind is, line number 237, line number 245, line number 252. What exactly these lines are doing? What's the purpose of these lines? And that is the core of writing a structure of node of an empty list. Okay. Quickly in the chat, I'm giving you 30 seconds. You can message to everyone. If you guys remember, we discussed very clearly what are these lines. 237 in Java, 245 in Python, 252 in C++. Answer in the chat once you guys are done, then we'll discuss. 30 seconds to 1 minute on the clock. Quick in the chat, guys. All right, guys, enough time. What's the answer if you remember? Let's go step by step. Is this the code of a linked list? Is this the code of a linked list? We discussed it during linked list also. Quick in the chat, guys. No, this is not the code of the linked list. This is the structure of node of a linked list. Okay. If you guys remember, I'd spent quite a lot of time on this to make you understand. There's a train. If you have to make a train, what is you need? You need to make compartments first. That is when you will connect them to make it a train. To make a compartment first, you need a blueprint of the compartment. This is blueprint of the compartment. Once you will execute this code, then you will get a compartment, multiple compartment like objects of this. Once you combine these multiple objects together, that is when you will call it as a train, which you are calling as linked list. So this is not the code of a linked list. This is the code of a blueprint of a structure of a node of a linked list. Or basically, this is the code of structure of a node of a linked list. This is not even a node. This is structure of a node. Okay. Now, what is interesting about these lines, which I said multiple times? This is inside my class node, I'm creating an object of the same class. Agree? Inside my class node, again, I'm creating an object of the same class. Inside my class or structure node, I'm creating an object of structure type or the same type. This is what you call a self-referential object. Usually you create a class, outside the class you create an object. You do not create the object inside the class. This is kind of a recursion for classes. Okay. What is that denoting is every class or every object made from this class will contain a schema such that it is referring to itself or it's replicating itself. Okay. Read this code again. Every object created out of this class will be replicating itself. Why replicating itself? It's a schema like this. It contains a data, which is integer. It contains a next, which is null. Okay. So data, which is integer, and a next, which is null. In that case, once you create node next equal to null, by default, this next will be of the same type as this one. Correct? This next will be of the same type as this one. So what will happen? The moment you create this next will be null. If you create another node, that will also contain the same structure, same structure, same structure. So every node that you will keep on creating, it will contains the same schema representing a data which is integer and a next which is of the same class type as the current class. Everybody clear with this? Cool. This is what we call as self-referential object. This is again self-referential object. This is self-referential structure here. You can make it in a class also, but just for understanding. Okay. Once you got this schema, how did you make a linked list out of it? If you guys remember, we create the first node, node first equal to new node, put the value 1, copy, paste, second, and third. So you got 3 objects created out of it. 3 object means now you got 1, 2, and 3. From your compartment blueprint, you actually got the compartments. How do you make a train out of it? You make first dot next equal to second, and you make second dot next equal to third. The moment you have done this, now you can say you have a linked list ready. Hope everyone remembers this. We discussed through in detail. I don't want to spend too much time on it. Quick in the chat, guys. Everyone remember this? Cool. Why did I say if you remember the code of a linked list, code of a binary tree is going to be cakewalk for you. Binary and a tree in general trees is going to be cakewalk for you. Why? Because it contains a very important property. The node that you're defining, it's replicating itself. Means if this is my node, let's say a linked list node, I want it to replicate to contain a data and a next pointer pointing to null. So there will be a data here, which is an integer type, and it should contain a next pointer null. Okay. Why this property is important? Because when I will make a binary tree or any kind of tree for that matter, I want a replicating structure. This is my root. It should have two children, left and right. These two children should also follow the same schema. It should have its own left and own right. Similarly, own left and own right. And this will continue to replicate forever. This part crystal clear to all. In a binary tree, I will have a node which will have a replicating structure. What do you mean by replicating structure? Every node will contain two children, and that will keep on going until we reach to the end leaf node. Why this concept we need to revisit linked list? Because we studied the concept of replicating structure or self-referential object, self-referential structure in linked list. That is why I did a quick revision here. So now when you go to the code of linked list, it will remain a cakewalk for you. Okay. That was it is important to revise. Plus, you got a revision of linked list again. Alrighty. Now let's come to the trees part. What do I need to change for the trees? Pretty much nothing. Structure of node of a binary tree. And what do we need to change here? We need to change the schema. So let's change the schema real quick. There you go. Last node. Only thing that I'll be changing here is integer data will remain the same. Node left will become null and node right will become null here. Now I got two replicas. Similarly, this will become self.left, self.right. Making my structure node star left, node star right. Nothing else would change. But now you are able to clearly visualize and understand this because we spent a lot of time in linked list part. Okay, so that is why it is saving time here. Everybody crystal clear with this. How do you make schema of structure of a node of a binary tree? Okay. If you have to make for any tree, that's pretty simple too. I already discussed in the code, but I'm writing down here also. Let's say if I have to make n array tree. So instead of two nodes, I want to make n number of nodes. If you want to make n number of nodes, what will you do? You'll convert into an array, correct? So you will make a vector of node star, call it as children, put the value L, initialize with null. That's it. That becomes an array tree. Easy. Okay. Now, once we understood how to create a structure of it, now let's write a complete code for a binary tree. Because this is still not a complete code. This is only defining the structure or schema of a node of a binary tree. Now we need to do various concept levels here. Concept level means how do we define the levels in a binary tree? Is that what you're asking? Yeah. So the levels we are going to define based upon the node that we're inserting. So since it is a binary tree, the moment I insert a third tree or the moment I insert a third node will become as level 2 and so on and so forth. So we follow 2 raised to the power h. Once we are able to insert it, that is what we'll define as a level here. Okay. So we'll see the complete code. How do we write that? Once we define the class node structure, this is my structure of node of a binary tree. Now let's actually build a binary tree out of it. How will you do that? Take this piece of code. What is this piece of code? It is this. So let's write down that as well. Easier for revision. Correct. That's what we're going to write now. Now I move to class main. Let's call this as public static void main. Inside my main, I'm taking string array of arguments. What next? First node that I'm going to create, let's call it as a root equal to new node 1. The moment you compile and execute this code, what will happen? My tree will contain 1. By default, this would be null. This would be null. All agree? Any doubts? Any questions? Quick in the chat. The moment I compile and execute this code, it will contain a root and root will have left and right to be empty. Next, if I say root.left equal to new node 2, now what will happen? Where will 2 be inserted? Click in the chat. Root dot left, 2 will be inserted here, and right value will be null here. Easy, all agree. What else? Root dot right, new node 3. The moment you say root dot new node 3, 1, 2, and this guy will become 3. Okay. Now what do? We got the root structure. We have defined the 3 parts. There is a concept of level. So root dot left, it becomes next level. If I say root dot left, it becomes level plus 2. Root dot left, level plus 3, and so on and so forth. Okay. Now, one more thing I'm going to write. You guys tell me what will be the structure of tree. Root dot left dot right, new node equal to 4. You guys tell me where will 4 be inserted exactly. Quickly in the chat. Come on guys, be quick. Structure of the tree. Just spell it out. Understanding. So if you look at this, 2 dot left, nothing is there. 2 dot right, that is where you're going to insert 4. 3 dot left, nothing is there. 3 dot right, nothing is there. This will be a structure of binary tree. Okay. That is how you write the complete code of a binary tree. First, you define the structure of it. Structure contains a left node and a right node and integer data. Then you create object of this to connect those nodes. Okay. You start with the root node and then you go on multiple levels down there. Everybody crystal clear with this. How do you make a binary tree from scratch? Okay. Now, multiple things, but before I go there, let me cover for all languages, then I will go deeper into the tree concept. When you say root dot left or root dot right, that dot concept is only in Java and Python. Okay. C++ guys, you will be using arrow operator. So you will say root arrow left or root arrow right. Dot is reserved for Python and Java. Reserved in the sense it's a syntax. Okay. Number one. So it covers the breadth. Every developer or every programming developer should understand. If you're coding in C++, you cannot use dot. If you're coding in Java, Python, dot is fine. That's what the syntax is. Number two, now once we covered the breadth, let's cover the depth part of it. So one thing we realized, we are able to create a binary tree from scratch. I can define the scheme. I can keep on adding as many nodes as want. But one important thing, if I have to add as many nodes as want, let's say I want to make the depth of the tree to be 10. So do I need to write root dot left dot right dot left right dot left right etc etc? JavaScript is fine with dot. You can define in JavaScript because everything is an object. So to the part, let's say if I have to create 10 different levels, should I write dot left dot right dot left dot right dot left dot right till 10 times? The answer is you can. There's nothing wrong with the code. If you write it, it will work for sure. Is it a good practice? The answer is no. It's not a good practice. So there is a way that you can take the array values and input and you can just parse it as a complete tree. So you don't need to go through that dot left, dot right kind of a thing. But even more important, in your actual interview questions, you will not be writing the binary tree from scratch. Just like you will not be writing the linked list from scratch. You will be given a binary tree and then you have to solve a question on top of it. I'll tell you both the ways, but I'm telling you very clearly, in your interview questions or in general, mostly in online assessment also, the tree will already be made. You don't need to do all of this. I did it because you understand, so that you understand everything from scratch. How a tree is made, how what happens in terms of object creation and how do you connect them. But you don't have to create a binary tree or any binary tree for that matter. A tree will already be created and given to you. Okay. All you need to do is you need to solve a question on that tree. Okay. But I'll answer the question or I'll cover that part in case you have to cover a tree. How would you do that? So your input from array, the formula that we follow is at ith index from the array, the children are considered to be 2 into I plus 1 index as left children and 2 into I plus 2 index as right children. What does that mean? For ith index element in an array, its children will be 2 into I plus 1 as the left children and 2 into I plus 2 as the right children. Let's understand this with an example. But again, repeating, you will never be doing it. Most likely 99% you will not be doing it. In interview, you'll be given a binary already and you have to solve a question on top of it. But just for your understanding, I'm telling you this part. Let's say my array input is 1, 2, 3, 4, 5. If I talk about index equal to 0, index equal to 0 will always be a root element. So 2 into 0 plus 1, which is going to be array of 1, which is going to be 2 here. That is going to be the left of root. And same thing, 2 into 0 plus 2, which is going to be array of 2, which is going to be 3 here. It's going to be right of root. Okay. If I talk about index equal to 1, so copy this. 2 into 1 plus 1 and 2 into 1 plus 2. This will become array of 3. This will become array of 4. This will become 4. This will become 5. Now, index equal to 1. What was there at index equal to 1? Index equal to 1 was left of root, right? So this is going to be left of root, which is 2. And this is going to be right of left of root, which is 2. So if I have to make a tree based upon this array input, my tree will look like this. We have 1. You got 2 and 3 as its child. 2 has 4 and 5 as its children. Everybody crystal clear with this? Quick in the chat, guys. I'm repeating it again. You will not be given an array to construct a tree, but let's say in a case if it is given, you should know how to create it. It's a simple formula. Ith node as a parent will have 2 into I plus 1 as its left, 2 into I plus 2 as its right. Okay. What you will be given is, and this is how you create a tree from scratch. What you will be given is this tree already constructed, and you have to solve questions on top of it. This is what you'll be given in the interview. Okay. All right. So we talked about the code of the tree. We talked about how to create a tree from scratch. So I'll mark this as done, which is already marked as done. Now we're going to talk about a very important concept, which we call as traversals. Okay, I'll remove that one part from here. And same part here. Traversal is a very, very important concept. Once we understood what are trees, what is real life application, how it is coded and implemented, now we're going to finally talk about traversals, and then we'll move down to the questions of or interview questions of binary trees. Alrighty. This was the last part of theory. Let's move to 429. Let's talk about traversals. What exactly is a traversal and why we have S here? What is this additional S representing? This additional S representing it's a multiple. So there are going to be multiple traversal. Why multiple traversal? Go back to our first principles. What did our first principle says? A hierarchical data structure is called hierarchical because there is more than one logical way of traversal. Okay, that is why we have more than one traversal way. There are two types of traversal in trees, graph, tries, pretty much all the hierarchical data structure. First is called DFS, which you call as depth first search. Second is called BFS, which you call as breadth first search. Okay. What are these? Depth first search can be further classified into three categories: pre-order, in order, post order. BFS has only one category, which we call as level order traversal. Okay, LOT in short. Now, we'll talk about DFS in detail, then we'll talk about BFS in detail. We'll write the DFS code right now, but we'll write the BFS code later. There's a reason behind that why I'm taking it later. Okay. Now, in order, pre-order, and post order. This is left, then you go to root, then you go to right. This is root, then you go to left, then you go to right. This is left, then you go to right, then you go to root. Okay. To understand all of these traversals better, in order, pre-order, and post-order, I'm going to take a sample binary tree. On that sample binary tree, I'm going to tell you what is going to be the in-order output, what is going to be the pre-order output, what's going to be the post-order output. And I will give you a shortcut trick to remember this in-order, pre-order, post-order, because I've seen people struggling remembering that. So I'll give a very simple shortcut trick. Once I'm done with these two, then I will give a binary tree to you guys, and you need to tell me the in-order, pre-order, and post-order for that. Okay, let's start with the one that I am taking first. A, B, and C. Okay, root is A, left is B, right is C. So if I talk about in order is what? Left, root, right. So left is B. What is root? A. What is right? C. If I talk about pre-order is root, left, right. So root, left, right. What about the post order? Post order is left, right, root. So left, right, root. Okay. Everybody crystal clear with this. For this binary tree, in order is BAC, pre-order is ABC, post order is BCA. Anybody has questions, please let me know. Quick in the chat, guys, shouldn't take this long. Easy. Okay. Now, before I give you a tree, which you will give me the answer for pre-order, in order, post-order for same, just want to make sure how many of you are actually interested in the trick. If you are comfortable, you don't need a trick. But if you feel like you might get confusion, which one is left root right, which one is root left right, I can give you a trick. Quick in the chat, guys. Okay, cool. I got the trick. Cool. See, guys, this is not trick as such. This is something I do for my understanding. And if you do it, things will become much easier for you as well if you try to go in the depth of it. So let's see. Simple trick is no English. As simple as that. Okay. Always make a thumb rule. Left always comes before right. Left is always going to be before right. That's thumb rule number one. Thumb rule number two, there are only three values, left, root, and right. So if you always know that left comes before right, there are only three possibilities. So if I look at this, there is left, there is right. You have to just insert root. Only three possibilities can exist. Either the root can come here, or the root can come here, or the root can come here. There is no fourth possibility. Agree? Quick in the chat, guys. If you fix the position of left comes before right, only three possibility can exist. Either root will be before left, or root will be between left and right, or root will be after right. There is no fourth possibility. And those three are exactly your DFS traversals. Now to remember where exactly the position of root comes, just remember this plain English. What does in means? In means in between. So my root will be in between. What does pre means? Pre means before. So my root will be before. What does post mean? Post means after. So my root will be at the end. So this pre, in, and post is denoting the position of the root, and left always come before right. So you put the root here, that becomes pre-order. I'm just calling it as root. So to differentiate between root and right. If you put the root here, that becomes in order. If you put the root here, that becomes post order. That's it. That's a trick. Once you understand the logic, you will never forget this. Everybody crystal clear with this? Cool. All right. Hope this is helpful. So you will never forget this again. Now coming back to the question that I have to give you. So I'm writing a simple binary tree here. You guys need to tell me the pre-order, in-order, and post-order output of it. 1, 2, 3, 4, and 5. To avoid any confusion, 1 has 2 children, 2 and 3. 3 has no children, 2 has 2 children, 4 and 5. Okay. What you need to do is you need to give me in-order output, you need to give me pre-order output, and you need to give me post-order output. Okay. Let everyone try. Do not message to everyone. Let everyone try and give the message directly in the chat to me. Do not message to everyone. Directly message it to me. I want each one of you to try it. Once you guys are done, just let me know. We can start the discussion. You need to give me the output in this format. I'm pasting that in the chat. Please change your message directly to me. Do not message to everyone. You guys can start giving your answers now. Okay. All right, guys. When you're done, just let me know. We'll start the discussion. All right, guys. Enough time. Are we good to discuss? Anyone needs more time? Are we good to discuss? Quick in the chat, guys. Yeah. Well, the interesting thing is I can see some wrong answers. If all of you are giving right answer, then that will actually ruin the purpose of messaging directly. But now I can see some wrong answer, which is good. Okay. It's good because you need more understanding in terms of clarity, and that's what needs to be done here. Okay. All right, let's start with the in-order traversal first. I think if you understand if you understand any one of the answer, rest of the answer will become correct by themselves. Okay, so let's focus on in-order traversal first. What does the in-order traversal says? In-order traversal says goes to left, goes to root, goes to right. Okay. So we talk about left. Should I define my left as 2 here? Because technically my left is 2, right? That is where the catch was. When you say go to left, it's always talking about the end of the binary tree, basically the leaf node. It's not just the first node. You're talking about left of the root tree. But do you check whether that particular node also contains a left? The answer is yes. So you cannot just stop at 2 and you can start traversal at 2 because you will not be able to come back from 4 to 2. So where do you need to start from? You need to start from 4, which is the extreme left. After 4, there is no left. So where will I start with? I'll start with 4 and then I will go to the root part. Everybody crystal clear with this? Quick in the chat, guys. Let me make a diagram also in case anybody is facing issues. See, this is your complete tree. Easier way is divide into multiple subtrees. This is my left subtree and this is my right subtree. All agree? This diagram, this understanding will make it crystal clear for you. When you say go to left, instead of full tree, go to your left subtree. So first I will do the in order of this left subtree, then I will come back to the root, then I will do the in order of my right subtree. Easy? Let's do it. So if I come here, I'll see it as left subtree in order. If I talk about only the left subtree in order, what will be the output? Quick in the chat, guys. Left, root, and right. So 4, 2, and 5. Okay. Then this one will remain as it is, and this one will remain as it is. Once you have done this, now writing a full in order becomes very easy. So now you take the left, you take the root, you take the right. So this becomes 4, 2, 5, 1, 3. And that is your correct output. Everybody crystal clear with this now. Any doubts, any questions, please ask. Everybody crystal clear with this. When you go to left, decide it is a left subtree and right subtree. Do the in order for left subtree, then go to root, then go to right. Okay. What about pre-order? Same thing. Pre-order, I have to go to root, so I'll start with the root first. Common sense. Root, then you have to go to left, then you have to go to right. So if I go to left, again I need to do a pre-order for the left child. So pre-order left child will be 2, 4, and 5. Then I'll come back, I'll do 3 here. Post order, you will go to right, left, root, and right. So if you go to left, again start with 4, left, right, and root. So 4, 5, and 2, then 3 and 1. That's it. Okay. This is your level order traversal or DFS. This is your DFS traversals in order, pre-order, and post order. Everybody crystal clear with this now. Quick in the chat. All of you are cool. Let's cover the second category, which we call as BFS traversal. BFS traversal is a level order traversal, pretty much straightforward, nothing much complicated here. I'll take the same tree for the reference. 1, 2, 3, one moment, 4 and 5. Okay. Why post order start with 4? It's 3, right? Why post order start with 4? Because you're going to the left. So leftmost will go to the 5. Then you go to the right. So 4, 5. That's why I start with 4. Okay. Always remember, left always come before right. Left always come before right. Okay. Alrighty, now coming back to this. If I have to make a level order traversal of this, how it will look like? Level order traversal is very straightforward. What you do is you go level by level, you travel from left to right, you print the output. So first level 1, second level 2 and 3, third level 4 and 5. Go level by level, print every values from left to right. DFS and BFS traversal, everybody clear? Quick in the chat. Is it okay to solve from root to bottom? What do you mean by root to bottom? Let me know what you mean by root to bottom, then I can answer that question. Okay. In order 213. 213. Solve again, solve 2. You say in order 213. Okay. Solve again, solve 2. I didn't get the question. What do you mean? One moment, I'll answer your question. Let me answer the previous question somewhere. When you say root to bottom, what exactly does that mean? So in order is 213, but you cannot go with the in order 213. Why in order is not 213? Because 2 also has children. So you have to go to the leaf node to start your traversal first, if that's what you're asking. You cannot take in between the non-leaf node. So you cannot pick any value from it and you can start traversal. You have to go to a leaf node. 213 has 2 children, which is 4, 5. No. That's not how you see it. You don't see as 213 has 2 children. 2 has 2 children, 1 has 2 children. So you started in an inverted format. So this is root. This entire is a left subtree, and this is a right subtree. 4 to 5, 1, 3. 4 to 5, 1, 3, yes, it's an order traversal. So you take it as a left. This is a left subtree. You do in order of this left subtree. Then you go to the root, and then you go to the right. Okay. Cool. Let me clear this. Let me come back. Now let me answer your question. BFS or level of traversal of BFS is pretty straightforward. What you do is now you travel the width, or basically now you travel your adjacent values. What do you define adjacent values in context of trees? In graph, we can define adjacent vertex, but in trees, when we say adjacent, we're talking about the same level. So what do you do in DFS or BFS traversal is go level by level, travel left to right, and print the output. So if I go to first level, output 1. If I go to second level, left to right, 2 and 3. Third level, 4 and 5. That's it. Okay. Alrighty, guys. This was our traversal, which is the most important part, DFS and BFS. Now, once we are good, now we're going to write down the code of DFS traversals in order, pre-order, post-order. We'll not write the code of BFS now. There's a reason for that. I'll write the code of BFS when I take an interview question related to BFS. Okay. But for now, we're going to write the code of BFS and then we'll move on to interview questions. So let's start with in order traversal, which is node root. First condition, you're going to check if my root becomes equal to null. Obviously, return from there if your root has become null. Condition is you go to left, you go to root, and you go to right. So in order root dot left, which is your left, you are going to print it. Let's say root dot data, whatever that value is, that becomes root. And then you go to right, which is root dot right. Okay. This is your in order. We can change the format to get pre-order and post-order. Pre-order again, root becomes null. What's the concept of pre-order? You take root, you take left, you take right. So starting with root first. So you're going to print the root value. You'll change the order of this. And then you go to left, then you go to right. Change the function, pre-order, pre-order, pre-order. All you have to do is you have to change these 3 lines. That's it. In order, pre-order, and post-order. Next, let's talk about post order. There you will have left, right, and root. So let's remove this part. You got post order, post order. You're going to bring this guy. You're going to bring it here, left, right, and root. Okay. Alrighty. Time complexity. Every node is traversed at once, so time comes to become big of n. Space complexity, big of n due to recursion step. Okay. Everybody crystal clear with whatever we have discussed in trees. Then we'll move on to interview questions. I'll quickly revise it where we are, and then we'll move on to the interview questions. Okay. This is where we. All right, guys. We have talked about trees and all the theory that we need to cover before we jump to the questions part. Type of trees. Number one, there are two types of trees, binary trees and n-ary trees. How do you define binary trees? A tree with a maximum of two children, which is 0, 1, or 2 for each node is called binary tree. There's a concept called leaf node. A leaf node is a node which does not have any children. How do you define complete or full binary tree? So specific binary trees are called complete or full binary tree. Basically, it's a subset where all the non-leaf node will have exactly two children. Okay. It follows a property for a level h or at a height h, number of nodes will be 2 raised to the power h. Okay. We talked about example 1 here, it's a binary tree and full binary tree. We talked about example 2, it's a binary tree but not full binary tree. Example 3, again binary tree and full binary tree. Number 4, it's a binary tree and full binary tree again. Okay. We verified that formula as well. Second category is n-ary trees, which we call as generic trees, where a tree with a maximum of n children for each node is called n-ary tree. Definition of leaf node remains same. Complete or full n tree, all non-leaf node will have exactly n children. Just replace 2 with n. This one you can see it's an tree, but it's not a complete n tree. This one is not an tree for n equal to 3. So definitely if it is not an tree, it can never be complete n tree. Okay. One moment. Isn't this also a case where all non-leaf nodes will have two children? Isn't C a leaf node here? Which line number? Which line number? 76. Okay, the example you asked for earlier. Well, if you go by the formula, the property 2 raised to the power h will not be satisfied here. So this ideally should be 4 values, which will not be considered here. That's why I said it's not a complete or full binary tree. Okay. All right. This was an tree. We discussed till this part and now moving to the code part. How line number 90 become full binary tree? How line number 90 becomes is 2 raised to the power h, two things. Non-binary tree, we are following the formula of 2 raised to the power h, which is 1. So this is h equal to 0. We always start with height equal to 0 here. And that is why this will be counted as a full binary tree. So a node, think of it like a tree which contains only the root node. If it is a root, by default, it's a complete full binary tree because you have the root. If it has one children and not the other one, that is when you will say it's not a complete full binary tree. But in this case, it is. Okay. We covered till this part. Yeah. In terms of a code, which will go to live down further also, this is what we generally define. If it is two children, you define left and right. If it is multiple children, you're going to define an array or a list like this. Then you move on to the application of trees. Application of trees is quite important. In any file storage system, no matter the operating system you're working on, you will find a file storage which follows in a hierarchical order. Those are implemented via trees. Ordering binary search tree is a special kind of a binary tree, which we'll talk about once we're done with questions of binary tree, which have search and access faster than arrays. So we use BSTs specifically in the case where we want to have a faster search. And BSTs are used in your indexing as well. All your SQL-based databases, for example, Postgres, Oracle, MariaDB, MySQL, the way the implementation of indexing works there because they implement binary search tree there. Okay, so real life use case here. Complexity of insertion and deletion in a BST is much better than arrays, but it's not as good as in linked list. But again, linked list has its own pros and cons. That's why. Since it's a dynamic allocation, there is no upper limit. You can increase or decrease the size of the tree at the runtime. Then we finally move to the code part. In order to understand the code part, first be clear about the linked list part. Why we need to revisit the linked list? Because we understood a very important concept, how to self-replicate yourself. Okay. How are we self-replicating in the structure of a node of a linked list? By this line, self-referential object or self-referential structure. Okay. Then we move on to the trees part. We have to do the same thing, but this time we have to replicate two times, left and right. So we add just one more line. This will be replicating itself. This become a structure of node of a tree, and this becomes binary tree, and this becomes structure of node of a n-ary tree. If you have to write the complete code, how do you write that? In terms of complete code, Once you have the structure defined, now you're going to define the children of that, or you're going to connect the trees out of it. Once you connect the trees, that is how your binary tree will be covered. I told you a trick. In terms of Java and Python, you're going to use dot. In C++, you're going to use arrow operator. I told you a trick. You will not have to construct a binary tree from scratch, but you should know how to do it. If, let's say, in 1% extreme cases, you're given an array to construct a binary tree, this is how you construct a binary tree from that. You don't need to write dot left, dot right till 100 times for 100 left. Okay. What you'll be given is you'll be given a binary, you will have to solve question on top of it. And you will be given the schema as well. So once we go to lead code, we'll see it more. But in general, you'll be given the schema. Schema will be pretty much the same. You will have left child, right child, integer data. Okay. Data can be called value or something else, but moreover, the structure would be same. And then you move on to the next important part, which we call as traversal. Since it's a hierarchical data structure, there is more than one logical way to traverse. One is called DFS, one is called BFS. So in depth first traversal, we do pre-order, in-order, post-order. In breadth first traversal, we do level order traversal. Okay. So we talked about DFS traversal here. It works left, root left, right to it. Okay. We got our output in order, pre-order, post-order. You guys given the answer for this one, so it looks all good. For BFS traversal, we have only level by level traversal. Go to first level, travel left to right, second level, left to right, so on and so forth. Finally, we write down the code for DFS traversal, which is in order, pre-order, and post-order. We talked about time and space complexity, so on and so forth. Okay. Now we are good to discuss our interview questions. We have around 40 minutes, so we're in a good shape. Okay. All right, guys. Everybody crystal clear? Then we can start with the question. Okay. If everybody is good, let's get started. So we have a question, we have a company, we have input, we have output. So I'll provide you the question, I'll provide you which company has asked it, I'll provide you sample input, I'll provide you sample output. Remember, you don't need to take input, you don't need to give output, you don't need to construct the tree. Tree is already there. All you have to do is, you have to complete the function that I will give you. Same goes in the interview also. You just need to complete the function. You need to mention the code, time and space complexity for sign. For the purpose of all our questions, structure of tree will be like this. It's a node. Node contains what? Node contains integer data. It contains a left child. It contains a right child. Even on the lead code also, this would be the same. The only difference is this node will be called as tree node. This data will be called as value. Nothing else. Everything else will remain same. Okay. Are you guys ready for interview questions? So we can start with first one quickly in the chat. All right, let's get started. Question number one. Asked in Amazon, and Amazon asked really a lot of tree questions based upon the tech stack that they have, because pretty much all the tech stack, they are extensively using trees and graphs. So you can take any interview question of Amazon, at least one question would be asked related to trees, and no surprise if they ask more than one. First question is height or depth of binary tree. A really useful question. Okay, so the input is 1, 2, 3, 4, 5, and let's say 6 here. 6 is the left children of 4. Can you guys tell me what is the height or depth of this binary tree? In meantime, I'll find this question on lead code as well. Put in the chat, guys, what is the answer? I'm getting this solution on a problem on lead code as well. Yep, here we go. All right, all of you have given the correct answer. Let me just pop the screen for lead code so we can get started on this. Moving this, let's move on to 3, should be good. All right. What's the answer now? The answer is just using DFS. Cool. If you have to collect the depth, I would say the answer should be DFS, not BFS here. Okay. The output is 4 here. Now, why the output is 4 is sometimes people confuse it whether I should count this as height 0, whether should I count as height 1. Okay. My answer is if it's an online assessment, it will be very simple, clear in the interview question or online assessment. If it's an interview question, confirm it with the interviewer first before making your assumption. 90% you will assume this to be depth 1. 10% some of the interviewers say consider this as depth 0. But either case, good to verify with the interviewer. So when you have a sample test case, you can see the output, accordingly you'll get the answer. Now, why the rationale behind keeping this as 1 instead of 0? The rationale behind this is, let's say if I have a tree which contains only one node, which is my root node. You can't define the height of this as 0. This height has to be 1, or depth, height or depth, same thing. Why height or depth, same thing? Height when you're looking from the bottom, depth when you're looking from the root. So if you're looking from the leaf, that is called the height. When you're looking from the root, that is called the depth. Okay. So output becomes 1 here. If you talk about an empty tree is where I will be denoting my height as 0. Okay. Null tree, it will be output -1. So that is what the concept or the rationale behind keeping the height as 1 here. Everybody clear? Cool. If it is clear, let's move on to the lead code question and then we'll talk about it. Okay, I'm answering it again. See, question was, at this level, should I start with height 1 or should I start with height 0? 90% in the interview, again, as I said, please confirm with the interview before making assumption. But 90%, as per my experience in interview, you'll be starting with height 1. Okay. Some interviewer might say start with height 0. Okay. So better to confirm first. What is the rationale behind height 1? That's what I'm talking about. If there is a tree which contains only a root node, the output is going to be 1, which is one length or 1 depth. If it's an empty tree, then the depth is 0. If it's a With that understanding, we got that I have to define the height equal to 1 for the root node. So if this become height equal to 1, this become height equal to 2, this become height equal to 3, this become height equal to 4. So the maximum height or depth that I got was 4 here. That's what I explained. Okay. Alrighty. Now let's move on to the lead code variation of it, and then we'll talk about that. Let's move to the lead code variation. Depth and height are the same thing. They have defined the definition also, but let's talk about it. Given the root of a binary tree, return its maximum depth. How do you define the depth here? You define the depth. A tree's maximum depth is the number of nodes along the longest path from the root down to the farthest leaf node. Number of nodes along the longest path from root down to the farthest leaf node. That is how you define maximum depth. Okay. Depth itself is just a level. Maximum depth is whatever the farthest you can go. So if you look at this binary tree, which contains 3, 50, 3, 9, 20, 15, 7. Which is the farthest leaf node from the root? This guy is my root. Which is the farthest leaf node from the root? Quick in the chat, guys. Both 15 and 7. When you say farthest leaf node, you're talking about the number of nodes you need to traverse there. So if I have to go to 15, let's talk about all the root nodes. 1 and 2. If I have to go to the leaf node of 9, I have to just traverse 2. If I have to go to the leaf node of 15, 1, 2, and 3. If I have to go to the leaf node of 7, 1, 2, and 3 here. Okay. So the maximum depth that I need to cover to travel to a leaf node, that is what you call as maximum depth of the tree. So the output becomes 3 here. Everybody clear why the output becomes 3 here? Quick in the chat, guys. Okay. You can also see the example that I told you. If you're given as an array, how do you convert that into a tree, or how do you visualize that in the tree? Same logic. 3 is the root. Root has the children of 9 and 20. 9 has null and null. Remember, 2 into I plus 1, 2 into I plus 2. So 9 has no children. 20 has 2 children. 20 left children will be 5 and 20 right children will be 7. Can you guys visualize the tree from the array itself? Same thing which I told you, 2 into I plus 1, 2 into I plus 2 trick. Quick in the chat, guys. Anybody questions, any doubts? Okay, cool. Everything is good. Let's wrap up the session here. There we go. Okay. Same thing I've mentioned here. Parent into I plus 1, parent into I plus 2. That was example number 1. Example number 2, you have 1 comma null comma 2. So 1 comma null comma 2, What is the maximum depth that you can go? You can go to, that's why the output becomes 2. Number of nodes are between 0 and 10 raised to the power 4. Means my tree can be empty. This is 0. It's a close range, means my tree can be empty. And values in the node are between -100 to +100. Does value in the node make any difference in my height of the tree? What value the node contains make any difference in my height of the tree or depth of the tree? It doesn't. Okay. Alrighty. If you look at the stats will speak for themselves. 5.4 million submissions means this question has been asked a lot many times. And if you look at the companies, lot many product-based companies have asked this question. Okay. Let's take the question first. Here we go. This is our problem statement. Go back to Sublime. This is a problem statement. Example 1. This is good. Example 2. So on and so forth. Maximum depth of binary tree, which is here. Okay, there you go. When it comes to the function that you have to complete, let's talk about that real quick. Okay, this is the function that we have to complete. Remember what I told you? You do not have to create a structure. The structure will be given to you. You don't have to create a structure. Okay, so you're given the tree. You don't have to create one. You just need to complete this function. You will be given the root of the tree, and you will be only given the root of the tree most of the question. Unless another integer or variable is required, most likely will be given only the root of the tree. You need to complete this function called max depth. What is it returning? It's returning integer. Integer denotes the maximum depth or height of the binary tree. Everybody crystal clear with this? Quick in the chat, guys. Cool. The structure of the tree node will be given to you. This is the structure of tree node. If you go to lead code on this link, you will be able to see that. So it contains a public class tree node. It contains the integer value, tree node left, tree node right, and some constructors, which you can ignore. But more or less, the node is called tree node here. Data is called value here. That's it. Nothing else. Exactly same. Alrighty, guys. Any doubt in the question? Anything which is not clear in the question? Anything which needs my input? Please let me know. If the question is crystal clear, type clear in the chat. Okay, everything is good. Let's get started. This is the lead code link, and this is the function that you need to complete. Feel free to code in any language of your choice and directly submit it on the lead code. Please share your submission link directly with me. Do not message to everyone. Do message or do write the time and space complexity along with the submission link you are sharing. Okay. That being said, everything is crystal clear from my end. Let's go ahead, directly start on lead code. Once you guys are done, share in the message to discuss, then we can start the discussion. Do not message to everyone. Let everyone complete that. Once you are ready to discuss, just post that in the message to everyone. Okay. Your time starts now. Once you guys are done, let me know. All right, guys, enough time. Shall we discuss? If everybody is done, shall we start the discussion? Quick in the chat, guys. Cool. Let's start the discussion real quick. The good thing is majority are able to solve and pass all the test cases, which is really nice. Now let's move to the actual implementation. Before the implementation, let's talk about the approach here. What is the approach? The approach is when you say you have binary tree, you're talking about two nodes at each level. One is left and right subtrees. Okay. For maximum depth slash height of tree, you need the maximum of left and right subtrees. Okay. So height or depth plus 1. This is the formula. Why 1? For the root node. So my formula becomes what? My formula becomes height or depth, whatever you want to call, 1 plus max of root dot left and root dot right. This becomes my formula. Okay. Let's validate on the sample input test case that we have and output as 4. So if we start with this, a quick dry run, let's start from bottom to top. I will take this tree. We're going to start now. So start with this. If I start with 6, the left node is 0, the right depth is 0, the maximum of 1 plus max root dot left, root dot right. So this becomes 1 here. Similarly, for the root node here, this becomes 1 here. Similarly, for the root node here, this becomes 1 here. Okay. So let's bring it here. Let's bring it here. What else? Let's bring it here and here. This good. Okay. Now, if I talk about 4, maximum of root dot left, root dot right plus 1. So root dot left, its height is 1. The root dot right, the height is 0. So maximum of 1 comma 0 is 1 and add 1 to it. So this becomes 2. All agree? Yes or no? If I talk about the height of 4, that becomes 2. We are talking from bottom to top. Okay. Similarly, if I talk about 3, in the case of 3, the left height is 2, the right height is 1. So maximum of 2 comma 1 is 1. Plus at maximum of 2 comma 1 is 2. Add 1 to it, that becomes 3. And now finally, maximum of 1 comma 3, left height is 1, right height is 2, plus 1. That becomes 3 plus 1, that becomes 4. That becomes a final output. This is how you calculate the height or depth of a tree. Okay. Before I move to code here, I'll just take a pause to make sure everybody is crystal clear. Remember again, in a binary tree, you have two trees. One is left subtree, one is right subtree. Your maximum depth can come from left subtree or it can come from right subtree. So what do? You find whichever has the higher depth. If left has a higher depth or the right has a higher depth, choose the maximum of that, then add 1 to it because root is not counted in it. As simple as that. Everybody crystal clear with this? Quickly in the chat. Come on guys, be quick. Easy? Quite intuitive. Let's write down the code for verifying this. So if we come here and move to this maximum depth, let's talk about the code real quick. Okay. What do we need to do in the code? We are writing this public integer maximum depth function. We'll define the base case. If root becomes null, return 0. I define left height. What I'm doing in the left height, I'm recurring on the left height. I define the right height where I'm recovering on the right height. Once I have left height and right height, I'm returning 1 plus math.max left height comma right height. That's it. Time complexity big of n, space complexity big of n. I'm trying to traversing every node at once. And since it's recursion, it will take me big of n recursion space. Just 3 lines of code. Any doubts, any questions, please let me know. Quick in the chat, guys. Easy. Let's compile this. Compilation is good. Let's submit this. Beats 100%, which is supposed to. When time as we discussed. Good. Space also big of n, as we discussed. Okay. Let's come back here. Let's take this piece of code. Let's add it over Sublime Text. There you go. Okay. Alrighty, we have done our submission. Now, we'll continue with the questions in tomorrow's session. Now we have only thing is to cover the question. We already covered the theory as part of this session. I'll quickly revise whatever we discussed as part of today's session, and then we can wrap up today's session. So this is done. Interview questions are work in progress. I'll keep it like this. Binary system will do after we are done with this. These are the list of interview questions. Cool. We'll resume with the questions tomorrow session. Today we have discussion about finalizing our theory of the trees and starting with the questions. Number 1, we talked about type of trees. We understood the difference between binary tree versus any tree. We talked about binary tree versus a full binary tree / complete binary tree. What's the property for that? 2 raised to the power h property in detail. Then we talked about, understood that with example. Then we talked about generic trees or NNA trees. Okay. So for generic trees or NNA trees, we talked about example for n equal to 3. We understood what's a complete NNA tree, what's a normal NNA tree, and we gone with the code part. Finally, move to the application of trees, understanding the PC file storage system, the purpose of BST to be used in indexing in SQL databases, Complexity is better in VST as compared to arrays, not as good as linked list. Then we talked about the code part. We revisit the linked list part because we need to revisit to understand the replication of structure. Once we revisit that, then we implemented the same using the binary trees. And same code goes for the NA tree also if you have to define a structure. Finally, we write down the code from scratch. If you have to create a binary tree from scratch, how do you do that? Okay. I told the syntax both in C++, Java, and Python, and JavaScript is similar to Java here. You can use a dot operator there. Anyways, to define an object for it. Then we talked about input from array. So in terms of input from array, if it is given as input from array, how do you construct a tree out of it? Okay, that trick also I've given. Then finally, we talked about traversal. It has two types of traversal, DFS and BFS, depth first search and best first search. DFS has three internal traversal, in order, pre-order, post-order. We understood the trick to identify all of them and how does the in-order, pre-order, post-order look like for a tree. Then we move on to the BFS traversals. We write down the code for DFS traversal. BFS traversal code will cover later once with the bio question. Finally, we start with the interview question. We have done the first interview question, which has been asked in Amazon and many other companies, which is maximum depth of a binary tree. So approach-wise, my binary depth or the height or depth is consist of two trees, maximum of left and right plus one. So we identified the formula and then we write down the code according to that formula. Time comes to big of n, space comes to big of n, beats 100%, pass all the submissions. Everybody crystal clear with today's session? Come on guys, quick in the chat. Everybody crystal clear? Cool. If everybody is clear, let's wrap up the session here for today. Let's catch up in tomorrow's session. They will be completing more questions of trees. Okay. The problem is solved. What was the traversal order? Good question. By default, if you look at it, we have not identified any order as such. I'm just going for left and right, and there it is root. Okay. So this is root left and right. Root left and right is what? Pre-order. Okay. This was a pre-order. Good. All right, guys. Everything is done. Any more questions before I wrap up today's session? Not good. Cool. Let's wrap up the session here for today. Let's catch up in tomorrow's session. There will be continuing with more interview questions of binary trees. Thanks for joining in. Have a good one. We'll catch up tomorrow.